Hey there, and welcome. For thousands of years, we've looked up at the night sky and seen these just absolutely beautiful curtains of light dancing above us. We're talking, of course, about the aurora. But what are they? Like, really? Well, today, we're going to unravel this incredible celestial light show, from ancient myths all the way to modern science.
All right, so let's dive right in by rewinding the clock. Way back, before we had satellites and all our fancy scientific gear, people still had to make sense of these amazing displays. And they did it the best way they knew how, with stories, with legends written right into the sky.
I mean, you can totally picture it, right? Silent, twisting ribbons of light snaking across the darkness. It's really no wonder that our ancestors looked up and saw powerful, mythical beasts. For some, they were a sign of good things to come. For others, an absolutely terrifying omen.
Now get this whole light show isn't just a northern thing. Up in the northern hemisphere, we call it the Aurora Borealis, the northern lights. But the exact same thing happens down in the southern hemisphere. It's just called the Aurora Australis, or the southern lights. It's a truly global spectacle.
And the stories people told? Oh, they were all over the map. Some cultures saw the lights and thought, hey, a royal baby must have just been born. Others believed they were the ghosts of the dead playing a game. And among some of the Inuit peoples of North America, there was this belief that if you whistled at the lights, they'd swoop down and snatch you away. But clapping your hands could scare them off. Wild, right?
Okay, so the myths are fascinating, but what's the real story? To understand what's actually happening in our atmosphere, we have to start our journey at the source. And that source is an incredible distance away. Our very own sun.
That's 149 million kilometers, or about 93 million miles. The origin of this breathtaking light show right here on Earth begins with something happening that far away. It's a cosmic connection on a scale that's, well, it's just mind-boggling to even think about.
So it all kicks off with something called the solar wind. This is a constant stream of super energetic particles blasting out from the sun in all directions. And look, this is not some gentle breeze, okay? It's a supersonic flow, rocketing towards us at speeds up to 1,000 kilometers per second.
So what happens when the supersonic solar wind, which is carrying its own magnetic field, just slams into our planet? Why aren't we completely blasted by this constant stream of solar radiation?
Well, it turns out our planet has its own defense system, a totally invisible force field that is absolutely essential for, life as we know it. It's called the magnetosphere. This is Earth's magnetic field, and it gets pushed and stretched by the solar wind into this long comet-like shape. It's like a protective bubble, a gatekeeper, and it deflects the vast majority of those dangerous particles safely around our planet. But, and this is the absolute key to the whole thing, it's not a perfect shield. Some of those particles get trapped. They get caught and funneled along Earth's magnetic field lines, spiraling down towards the polar regions. This creates a ring of intense activity that we call the auroral oval. Okay, so the particles have made it past the guards, they're spiraling down. Now what? How do we get from a stream of invisible particles crashing into our atmosphere to that incredible palette of vibrant dancing colors?
Well, the magic happens through a process called atomic excitation. It sounds complicated, but it's pretty simple. When one of those solar particles, usually it's an electron, slams into an atom in our atmosphere, it gives it a jolt of energy. The atom gets all excited, and it can't hold on to that extra energy for long, so it gets rid of it by releasing a tiny particle of light, called a photon.
Seriously, you can think of it as being the exact same principle as a neon sign. In a sign, you pass electricity through a gas, the atoms get excited, and bam, they release light. The aurora is just a planetary-scale version of that. It's powered by the sun, and it's using our own atmosphere as the gas in the tube. So why all the different colors? Well, it all boils down to two things. What kind of atom gets hit and how high up it is. That classic vibrant green color you see most often, that comes from a collision with an oxygen atom, about 100 kilometers up. But if that same type of oxygen atom gets hit way higher, we're talking above 200 kilometers, it glows red. And then you have nitrogen in the mix, and that's what adds the beautiful blues and deeper reds. So the aurora is beautiful, for sure, but it's not always this gentle, graceful dance. Sometimes it's the visible symptom of a much more violent event, a massive disturbance in Earth's magnetosphere that we call a geomagnetic storm.
And the amount of energy we're talking about here is just staggering. A single auroral substorm can release hundreds of terajoules of energy. To try and put that into perspective, that's as much electrical energy as the entire United States consumes in over 10 hours. all unleashed in our upper atmosphere.
And this is why it all matters, beyond just the pretty lights. That energy has to go somewhere, and it can have huge, real-world consequences right here on the ground. These storms can cause surges in power grids, leading to massive blackouts. They can disrupt the satellite communications we depend on, and even mess with the navigation systems in our cars and planes.
So, because the stakes are so high, scientists don't just admire the aurora. They are constantly studying its cause. To forecast these space weather events, they're always monitoring our planet's invisible shield, measuring every little fluctuation in the geomagnetic field.
And one of their main tools is something called the K-index. It's a pretty simple scale. It just goes from 0 to 9, and it measures how much geomagnetic activity is happening. A low number, like a 1 or a 2, means everything's quiet. But when that index climbs up to a 5, that means we're in a storm. And if it hits a 9, yeah, that's a major event, and that's when you brace for impact.
So, from mythical dragons in the sky to real-world geomagnetic storms, the aurora is this constant, beautiful reminder of our deep and sometimes volatile connection to our sun. Isn't it just incredible that a storm happening 93 million miles away can travel all that distance to paint our sky with light and, at the same time, challenge our most advanced technology right here on the ground? It's amazing.